Awesome. Thanks. So yeah, hello everybody, and welcome to another astrophysics seminar. It is my absolute pleasure to introduce Catherine Fielder. She is a postdoc at the University of Arizona now. So she's joining us bright and early at 8 a.m. her time.
Yes.
So very much appreciated for making it out so early. But yeah, she was a PhD student at the University of Pittsburgh, where she worked with, as you can see, Jeff Newman, Brett Andrews, and a few others, and has done a lot of really cool work on dark matter halos, dark matter substructures, the Milky Way, and so on, all of which she'll be talking about today. So yeah, without further ado, feel free to take it away.
Yeah, thank you for the introduction, Stacy. Yeah, I'm really excited to be here, and I appreciate everyone accommodating the kind of unusual time, but I very much so appreciate it. So I'm going to be really highlighting a lot of the work that I did in the second half of my PhD. So this is predominantly more on the observational side. And this is work done at the University of Pittsburgh, and now at the University of Arizona, I'm kind of diving back into the smaller size galaxies and dwarfs, which I'll touch on very briefly at the end. But yeah, all right, there we go. So I'm going to just start off by showing you the punchline and kind of try to keep you hooked with it, but showing you the first ever UV to IR SED of the Milky Way, and I'm showing that here. This is essentially brightness.
I think we're seeing your slides. We're not seeing your presentation view.
Oh, let's see. Let me try again. See, is this any better?
Yes. Yeah, that's better. Thank you.
Thank you for letting me know that. Yeah. Okay, so this is our first long baseline SED of the Milky Way, and the Milky Way points are these black points shown here. Later on, I'll explain in a lot more detail how we get to this. It's just compared to a couple other spectra of other local galaxies, but as you can see, we have a pretty realistic looking prediction for what the Milky Way might should look like at a variety of wavelengths, which is really exciting. So the Milky Way itself offers a very unique perspective on our understanding of galaxy formation evolution. It's kind of the best laboratory for testing our theories, and it's our benchmark for comparisons, where you have things like very detailed looks at the creation of stars in nearby stellar nurseries and stellar samples. This is an example of that. And we also have observations of colors and magnitudes from several surveys, as well as spectra, distances and proper motions from Gaia, which you can kind of see here in this kind of cool little GIF. And then we also can study satellites around the Milky Way to test dark matter theories. And then, of course, simulations, which allow us to extrapolate anything that we're viewing within the Milky Way to potential evolutionary histories, testing our actual understanding of galaxy formation evolution. And so, as you can see, this is kind of an actual image that we have of the center of the Milky Way, and this is a simulation version of the Milky Way. And so we're definitely at the point where we're creating simulations that do seem to represent the Milky Way. But we kind of want to understand exactly how the Milky Way fits into other galaxies, general galaxy population, in order to understand, like, are simulations actually creating results that we should have, or are they just tuned in a specific way, maybe the incorrect way, to make the Milky Way that we have from the simulations. So there's lots of different galaxies, and really my work that I'm focusing on talking about today is kind of putting the Milky Way in that context. So the idea is that we want this outside-in view of the Milky Way. In external galaxies, we can measure a lot of bulk properties relatively effortlessly, things like color and luminosity, but we can't measure these in the Milky Way because we can't really step outside of it. And so simulators are kind of left to compare their simulated Milky Ways to a general galaxy population that we think represents the Milky Way, but may not necessarily be a good test to really nail down some of the details in those now very accurate simulations. So just a quick review of the general galaxy population. We have our elliptical galaxies. They're quiescent, as in they're not forming stars, very few morphological features. We have our spirals, star-forming disks, things like the Milky Way. And then we have the kind of unusual category of things that are maybe disks without spiral features, or products of mergers, things like that. So recent research has kind of pointed to the Milky Way seems to be a little bit more unique than we initially thought of, like this beautiful, blue spiral interpretation of the Milky Way. And so kind of a key result is the kind of expected quiescent merger history of the Milky Way. We have this understanding from both simulation and observations. A lot of my earlier simulation work was studying dark matter halos with properties similar to the Milky Way, where the properties that we see are reflective of a somewhat relatively inactive merger history. And additionally, observationally, the scale length of the Milky Way's disk appears to be relatively compact compared to other galaxies of the same luminosity and mass. So this is a plot of a galaxy scaling relation where we have I-band absolute magnitude as a function of disk scale length. This is a general galaxy sample. And then we have this point of the Milky Way where it's kind of outside of this 2 sigma region. So we need a better picture of the Milky Way to actually make our comparisons from simulations to observations. So I'm going to kind of quickly remind you all of 2 methods that we use for studying galaxy populations. The first is spectral energy distributions. So these are a really great way of understanding what's within a galaxy, because of the different physical processes occurring within a galaxy are kind of imprinted at different wavelengths on the SED. So you can see this SED bottled from this galaxy NGC 891, where you can see this is where the stellar population dominates. This is, for example, where then the dust dominates. So you kind of get the general constituents of what's within a galaxy. And that's kind of what that bullet point's saying. But it's a really fantastic way of kind of inferring the different things that have occurred within a galaxy. The other tool that we use is the color bimodality of galaxies. So here is kind of a cartoon of that, where you have color versus brightness, and galaxies kind of separate themselves out generally on this type of diagram. And we believe that this is a consequence of galaxy evolution that is a very convenient and easy way to compare general galaxy populations to each other. So the red sequence has those kind of elliptical galaxies I showed earlier, as well as lenticular galaxies, which are just disks without any other morphological features. And so these are the objects that, because they're not forming a lot of stars, they look very red. On the other side is the blue cloud, which has your kind of standard spirals and some irregular galaxies, things that are undergoing star formation. Because of that, they appear to be more blue. And then you have this kind of strange region in between that has often been called the Green Valley. So this could be a few different populations of galaxies. Maybe they're late type galaxies that had their star formation quenched, or they could be early type galaxies that had their gas reservoirs rapidly destroyed. Either way, these are kind of it's kind of the unusual region on the color luminosity diagram. And I just want to emphasize galaxies could potentially move around this diagram. Of course, you could have something that starts as a star-forming galaxy, become quenched, and become, move from the blue cloud to the red sequence, for example. So I want to put the Milky Way on these kinds of plots. First, compare the Milky Way's colors of brightness to other galaxies, kind of understand how it compares to a general galaxy population, and also try to make this SED for the Milky Way. So prior constraints on the colors of the Milky Way come from something called Milky Way analogs. This was a lot of work done by a prior graduate student of my PhD advisor, Jeff Newman. So this is work done by Tim LeQuay. And so what he looked in SDSS and found galaxies that shared some sort of properties with the Milky Way. So the idea is that if the Milky Way has the same mass and star formation rate as another galaxy, then they should also share photometric properties. And so he did this specifically in the optical wave bands from SDSS to ugriz, and so was able to make kind of these color brightness plots similar to what I just showed you for the sample, as well as make a prediction using the Milky Way analogs of what the Milky Way's color should be in the optical. And so that prediction is shown here with kind of your comparison of the blue cloud and red sequence kind of illustrated to help guide your eye. So you see the Milky Way kind of seems to be not exactly where you might have originally expected it to be in this kind of region. And it appears to be more so a Green Valley type object. But the optical kind of limits our view of the galaxy. So what I've plotted here are SEDs of a few different galaxies. So this darker blue is a spiral galaxy. This green is an interacting galaxy. This purple is another spiral. And then this very light, like turquoise color is an elliptical. And I want to emphasize that morphology does not directly tell you what an SED is going to look like. But what I want to illustrate here is just that different SEDs look very similar in the optical. So I've kind of shaded in now the regions that are in the UV and near and mid IR. And you can see it's very hard to disentangle these galaxies from one another. They're quite similar, except for some of these emission lines, but we won't get that from just an SED, unfortunately. But the optical bands just don't quite cut it for disentangling SEDs. So we want to extend to other wavelengths to get better constraints on our understanding of the Milky Way. There are also other galaxy parameters that we can look at, not just stellar mass and star formation rate, that we can also easily measure in other galaxies and make inferences for about the Milky Way. So things like bulge-to-total mass ratio, which is just the ratio of the bulge mass to the total mass of the galaxy. And so what I've shown here is a plot that we made of bulge-to-total mass ratio versus star formation rate with two different samples of Milky Way analogs. In red, you see the stellar mass star formation rate Milky Way analogs, and in blue, you see the stellar mass bulge-to-total mass ratio Milky Way analogs. And so when one of the parameters of these three is not utilized, they span very large space in this third parameter space. So once you add this third additional parameter, you very strongly constrain a lot more of what kind of range the Milky Way can fall within, or we expect the Milky Way to fall within. Other properties we look at are disk scale length, which I mentioned previously. It's a very important, another important tool that we have at our disposal. We can also look at things like bar presence, or if there are other parameters you were interested in, those could also be looked at. So these are especially important to utilize because the Milky Way does seem to be atypical amongst its peers. And so it's useful to have these additional parameters to kind of better constrain, what do our Milky Way analogs look like. So this is just a quick view of what the sample looks like. So we use a lot of different catalogs to get our data. The parent sample is from SDSS. And then we have our stellar masses and star formation rates from MPA-JHU. And so this is what was also done in the previous Milky Way analog studies. I've added a bunch of additional catalogs to get additional wavelength ranges, as well as for additional measurements. And in addition to the prior parameters that were looked at, stellar mass and star formation rate, I've added in bulge-to-total mass ratio, disk scale length, and bar probability. We also use axis ratio as parameter. I'm going to talk about that a little bit later on, but basically we want to be looking are making predictions for face-on galaxies and using properties from relatively face-on galaxies. And I'll talk about that why in a second. So circling back to analogs. So this is a great diagram from a collaborator of mine, Nick Boardman, from a paper a couple of years ago, where he kind of just went through the process of, as we add more parameters, how many Milky Way analogs do we have? So you start with an initial sample of 21,000 galaxies. So if you just do a cut for stellar mass, you decrease your sample by an order of magnitude. So then as you then add a second parameter, regardless of what it is, you again decrease your sample by an order of magnitude. If you add the third parameter in, again, you're decreasing by an order of magnitude. So by the time you have all four parameters of mass, star formation rate, bulge-to-total mass ratio, and disk galaxy, you end up with 0 analogs, which is bad. And so the culprit for that is that there are actually not a lot of galaxies that are super similar to the Milky Way, which is not completely surprising. Right? Every galaxy is a little bit unique. So what I'm plotting here seems a little confusing, but it's basically the number of galaxies with it less than whatever sigma that I'm plotting. And then these are, within X sigma of the Milky Way. So if I'm looking at objects within 2 sigma of the Milky Way, you actually don't end up with anything that has bulge-to-total mass ratio, that has disk scale length and bar measurement of expected to be a bar. And so kind of what we're seeing is that, within 3 sigma at 5 parameters, you only get 10 Milky Way analogs, which is not good. So the Milky Way analog method scales very poorly with increased dimensionality. So the workaround for that is to not use Milky Way analogs, but something called Gaussian process regression. So a Gaussian process regression is a type of interpolation, and the information is accounted for by something that we call a kernel, which just defines the types of functions that are used to describe your data. So let's go back to thinking about a regular regression. You're trying to find a function that represents your data set as closely as possible. And Gaussian process regression does this, but in a probabilistic way by using both the kernel and then the different points you have constraining the parameter space. So instead of calculating the probability for a very specific function, Gaussian process regression does it over all functions that could fit your data. So not only are you getting a function that describes your data, then you also have errors on any prediction you make. So you have these, this is a one-dimensional Gaussian process regression shown here, where you have a few constraining points. And so, if you think of just these 5 points, there's many numbers of functions that could describe this data. And those many functions are what are used to determine kind of this error region in the less constrained parts of the parameter space. And so what's great is that you can predict a value and uncertainty of the quantity that you want at any arbitrary point in space after you've applied the kernel to the training data and optimized it. So this is a type of machine learning, but it's actually very accessible and easy to use. You could sit down and write a Gaussian process regression in less than a day. So what do we do with this? So to predict photometric properties, we train the Gaussian process on the galaxy properties that we measure in both the Milky Way and external galaxies. So these are your stellar mass, your star formation rate, your bulge-to-total mass ratio, etc. Then we fit the Gaussian process model for a photometric property that we measure in the external galaxies. So these are your G minus R band color, or maybe your I band absolute magnitude. And so those are what we are trying to predict for the Milky Way, which we do by kind of essentially inputting what this estimated parameter is for the Milky Way, getting out what the Gaussian process predicts the photometric property will be. So I've kind of worded that in a weird way because we actually also want to account for the errors on the predicted Milky Way kind of physical properties, if you will. And so we actually draw a bunch of times from a probability distribution function of the different Milky Way physical properties to make these predictions. So just kind of what does that look like comparing the Milky Way analog technique to the Gaussian process regression technique? So what I've plotted here is G minus R rest frame color as a function of stellar mass. So the orange points are your Milky Way analogs, if you will, and this is only for a couple parameters, but just as an illustrative purpose. So using stellar mass star formation rate. So you can see your analogs are very close to the stellar mass of the Milky Way. And this orange star and error region are predictions from Milky Way analogs. But with Gaussian process regression, you actually train from the entire parameter space. So you're not limiting your window to just things very close to the Milky Way. And so you have a function that describes this parameter space. And so you can make a prediction once you put in the stellar mass and star formation rate of the Milky Way, you get this G minus R color prediction. You can see they're actually quite similar to each other, which is great because we don't expect them to be different when using kind of the same type of parameter space. So let's look at some results from using Gaussian process regression, comparing the Milky Way to other galaxies. So I'm going to step through this in the optical first, because this is how we compare our results from the Gaussian process regression to the results determined from using Milky Way analogs. So what I've shown here, it's U minus R rest frame color versus stellar mass. These contours are just our main galaxy sample. For illustrative purposes, I've kind of drawn in approximately where the red sequence of blue cloud would lie, just to kind of help you parse the diagram. And so we can also draw these kind of arbitrary lines of estimates about where star forming, green valley, and quiescent galaxies should lie according to in optical color space from Schwinski et al. 2014. So then this little error bar that I've shown in the corner is just the mean uncertainties of galaxies in the sample. So I can plot on the prediction result from previous work using Milky Way analogs shown here in orange. And then I've also plotted now our prediction using all 6 parameters, stellar mass, star formation rate, bulge-to-total mass ratio, disk length, all of this from the Gaussian process regression and the 1 sigma region. So I've noted here that this is for a face-on Milky Way, and I can make this same prediction for a edge-on Milky Way, but let me explain what that means. So inclination reddening is an effect that we observe in galaxies, where if the colors that we see from an external galaxy viewed edge-on are different from the ones viewed face-on, because we're looking at a lot more gas and dust. It makes the galaxy look more red than its actual intrinsic colors. So we kind of can't necessarily trust the measurements we make of these edge-on galaxies, because it's not their actual intrinsic colors or magnitudes. And so our proxy for inclination is just axis ratio, where essentially the B over A of about 0 is something edge on, and B over A of 1 is about face on, which is a pretty good approximation, surprisingly. And so this is a parameter that we utilize in the Gaussian process regression, where if I instead said, well, what would it look like for a tilted Milky Way, I can make that prediction as well. And you can see it does look redder and move into the red region, which is kind of cool that we do that. But overall, kind of backing up again, so the results from Milky Way analogs are pretty similar to the results we get from Gaussian process regression. And don't worry about the different predicted or estimated stellar mass of the Milky Way. We just have better constraints now, and that's why that number has changed in the X direction. And it's another optical plot now with just G minus R color instead of U minus R. The overall picture that we're getting here is that we have consistency with previous results, still that the Milky Way should be relatively bright and redder than your average spiral galaxy, or something that we would say is kind of within the region of being in the Green Valley. So now we can start actually compiling together our SED and making that beautiful full SED that I showed you right in the beginning by putting on our little optical points. And so what I've showed here are just a few templates, and generally templates are just averages of a few galaxies, in this case of these specific types of morphologies. But like I said before, morphology is not directly correlated to a specific SED shape, so I think the labels are a little misleading, but they are a useful first pass comparison to see if we're getting reasonable results. I've also plotted the full spectrum for a spiral galaxy that's often compared to the Milky Way, just also as a comparison. And that's this bad boy. So we put all those optical points. Now, like I said, we need more than just the optical. So let's look at the ultraviolet. So this is a plot of rest frame NUV minus R from GALEX as a function of specific star formation rate. And so in these kinds of plots, Samir Salim has divided them into many regions where you have your star forming regime in terms of specific star formation rate, and your transitional and passive. And then in terms of NUV color, you also have kind of your green valley, your quiescent objects, and your star forming objects. And so you already see the point that I've plotted for a prediction for the Milky Way. It looks a little bit different than what we saw in the optical. So in contrast, the Milky Way, while near these transitional regions, is actually on the star forming side of the green valley in the UV, and it's outside of this transitional region in terms of specific star formation rate. So unlike in the optical, the Milky Way is not as quote unquote red, and by red I mean quiescent in the UV, and does not lie at the saddle of the distribution like it did before. And so this is likely driven by current ongoing star formation within the Milky Way. We know the Milky Way is still forming stars at a somewhat decent pace. And so that would make the colors in the UV to be relatively blue, quote unquote. We can make same plot for the far UV from GALEX and get very similar results. So now we can step back again and add these points again onto our kind of template SED comparison shown here. So interestingly, it seems like it's starting to trace kind of this SBC morphology, which interestingly is probably similar to the Milky Way's morphology. But again, I would take this with a grain of salt. So last but not least, let's look at the infrared. I'm specifically showing plots here for the WISE mid IR, but you can also make these plots for the 2MASS data that I use. So the infrared results that you're seeing are relatively similar. So what I plotted here is just a WISE color plot. And we again have these kind of dividing regions of star forming, and then something called the infrared transition zone and quiescent, defined by Al-Talo et al. 2014. Here's our Milky Way prediction. So the Milky Way is likely forming enough stars that, again, it looks bright in the IR, as in it is outside of this infrared transition zone and in this more star-forming region due to the dust re-emission. So the infrared transition zone itself is similar to what we've coined the Green Valley in terms of optical colors, but galaxies within this range typically have already turned optically red. So the idea is that maybe the infrared transition zone lags a bit behind what is occurring or what you're seeing in the optical. Okay, so now we can put our infrared points on our kind of SED comparison. So this is great so far, and this is our sigma for R band magnitude because we are normalizing in R, and so this would be kind of added in quadrature to all of our points, but we don't plot it. But so you can see with these templates, they're not that great because they don't include, say, like mid or far IR information, so that kind of seems to be lacking and what that traces. But overall, we can see that GPR makes results comparable templates. So that's already great, right? At least we have something comparable to averages of SEDs. But again, these templates are great comparison, especially because of the lack of bias, and also because these templates are averages about a handful of galaxies, 5 maximum. So it's not that informative. So let's compare to actual nearby galaxies. And that's what this plot that I showed you at the beginning is. So again, it's very similar to the previous plots I've been showing you, but instead of showing those templates, I'm just showing a few actual galaxies from the Brown et al. 2014 Nearby Galaxy Atlas. And this had a total of 129 galaxies. And I did a very basic comparison here. So the first thing I did was kind of just not look at any of the galaxies that were edge on. And we kind of have a criteria of if it's, inclination is greater than 0.5-ish, we say it's relatively face on. And then I just did a very basic chi-squared comparison to all of the galaxies that remained. And so that's kind of showing that there's some other galaxies that are within the 68th percentile in terms of chi-squared. And then these 2 galaxies were the most close match to the Milky Way itself, which is cool. And overall, we can conclude that the GPR is able to predict results that look similar to both SED templates as well as individual observed SEDs, which is awesome. And so I kind of teased a little bit about how we can look at, say, a different inclination for the Milky Way in our predicted results. So what I'm showing here is an SED. Again, these points are predicted SED for the Milky Way. And so I've trained the Gaussian process regression on these 6 what I'm calling like structural parameters of stellar mass, star formation rate, etc. So I hold all of those the same. I say we're keeping this at the fiducial value for the Milky Way, but now I'm going to put in a variety of inclinations and see what type of prediction we get out for the SED. And so we actually very nicely in the Gaussian process regression capture the effect of inclination reddening on the SED, whereas you get more and more edge on, you're getting less and less bright especially in the UV and also in the optical. The near IR has very minimal change, and then you start to see an actual brightening in the mid IR that's likely related to this re-emission from dust. That's kind of summarizing what I said, but it's really interesting how you can kind of capture these types of effects with these kind of more machine learning types of models. And I do want to emphasize, while I have done this exercise and gotten reasonable results, we still don't think that parameters measured with inclinations below around 0.6 or 0.5 are not very reliable. So it's actually pretty great that we still are able to kind of capture this effect. And you could actually do this with all of the parameters. And a lot of people say this is the most exciting plot, which I kind of agree. So I have this SED I just showed you. The rest of these panels are residual SEDs. So I'm then just dividing by the actual SED of the Milky Way. So this is, again, inclination in this bottom panel. So if we divide by the Milky Way's SED, that would lie at 0, shown here. And then you could even more clearly see kind of how things separate out in, say, especially in the UV and in the optical, and then, of course, in the mid-IR. And so now we can do that same exercise again and say, what if we kind of modulated the Milky Way star formation rate, kept everything else the same? So now we're kind of cycling back to inclination should be 0.9, and we know the other parameters of stellar mass, etc. And so you can see that if the Milky Way had a higher star formation rate, it would be even much more brighter kind of across the board, but especially in the ultraviolet and the mid-IR. And we can kind of look at this same type of plot for disk scale length, bulge-to-total ratio, and even our bar counts that we're using from Galaxy Zoo 2. Now, some of these results are a lot smaller, especially in these two lower panels, especially for things like bar, whatever way the bar affects the galaxy is, very closely tied to things like star formation rate. And so a lot of the effects that might come maybe from modulating the bar are already incorporated in things like star formation rate. So that's why kind of the effect seems to be relatively minimal when you modulate it. Okay. So we've confirmed that the Gaussian process regression produces sensible results, and we have an SED of the Milky Way. So what can we actually say about the Milky Way? So this is a population of galaxies called red spirals in this upper row. So this is from Masters et al. 2010. So these are your kind of regular blue spirals, and these are red spirals, which you can kind of tell exactly why they're named as such. So for galaxies with stellar masses above 10 to the 10 solar masses, which the Milky Way falls within, it's relatively massive. So the optical blue cloud and red sequence overlap. So this is a diagrams from Samir Salim's 2014 paper. So you kind of have this overlapping region here. So these are galaxies that probably underwent a majority of their star formation early on compared to their kind of less massive counterparts. And that's why they look optically red, because the optical colors are generally reflective of your average stellar population. If the average is old stars, it's going to look relatively red. Red spirals are also UV bright. They're still forming stars, although typically at a rate that is lower than blue spirals. So we can actually compare, this sample of red spiral galaxies from Masters 2010 that overlap with our galaxy sample to the Milky Way. So showed here first is the UV color versus specific star formation rate plot that I showed you before. Now all of these red points are the red spiral galaxies from the Masters 2010 sample that overlap with our sample. You can see that the Milky Way kind of seems to fall acceptably well within this kind of sample. We do the same for the optical, and you see again the Milky Way is kind of in this region. And again, in the infrared, that the Milky Way is kind of falling into this regime, which is very cool. So it seems to be the case that the Milky Way is relatively consistent with a population of galaxies called red spirals. We can actually dive into that even further and plot the SEDs of these galaxies, since I have all of their photometry. And again, we're seeing that, these black points are the Milky Way. These red lines are the different Masters et al. 2010 red spirals. And they kind of fall or nestle within the region of Milky Way's SED. Obviously, there's a bit more noise within the UV and relatively further WISE bands, but overall it seems to trace pretty well. And if you're curious in general about these WISE bands, they have a pretty bad signal to noise in general. And so that's why their error bars are quite large. And we also see that they can actually be a pretty important discerner when comparing SEDs. So I think that's also something to think about in the future of improved modeling of constraining the WISE bands or future surveys. So let's actually dive in and compare the parameters from red spirals to the Milky Way. So Karen Masters kind of selected a color cut guided from prior studies of what red spirals probably fall within. So if we make this same kind of quick analysis for our predicted colors and absolute magnitude in R band for the Milky Way, it falls well within what you would expect, where you're just looking for a G minus R color that's greater than, this number minus something primered by the R band absolute magnitude. And the Milky Way is within that, as in the G minus R color is definitely greater than what you'd expect from, this little expression here. So red spirals are more likely to be the massive and luminous compared to the blue spirals. And we've already seen that in the color magnitude diagrams that I've showed you, especially in the optical, for example, where the Milky Way looked quite massive and bright compared to your average star-forming spiral. And then, so red spirals are, like I mentioned before, UV and IR bright. Their star formation rates on average are around 1 solar mass per year. There is some variance. There are some that are even up to more than 10 solar masses per year. But in general, relatively low star formation rates. And the Milky Way does fall within that. Its star formation rate is about 1.65 solar masses per year. And like I said before, it's UV and IR bright compared to the optical consistent with this sample. Also, interestingly, red spirals seem to have a relatively high bar fraction. 70% of the red spiral sample have bars compared to 27% for an average blue spiral population. And we know the Milky Way has a bar. How strong that bar is up to debate, but it's I think mostly agreed upon, at least for us in the SDSS Milky Way as a galaxy group, that Milky Way has a bar. And in fact, perhaps the bar could be connected to why these spirals are red, but I think our understanding of exactly how the bar affects galaxies is kind of contentious between different groups. It's kind of hard to say. But things seem to be pointing to that the Milky Way looks like this red spiral type of galaxy. So just to conclude, I've determined the luminosity for the Milky Way using GALEX FUV NUV, SDSS ugriz, 2 mass JHKs, and WISE W1 through W4 bands in a self-consistent way. So this has kind of given us our first ever constraints on the actual spectral energy distribution of the Milky Way. And so this is very important, kind of circling back to what I was saying in the beginning. So now hydrodynamical simulators can tune their parameters to produce galaxies with, SEDs that match what we predict for the Milky Way in a more consistent way. Instead of just saying, well, we think the Milky Way kind of looks like this, so this seems right. And now we have a better constraint for simulators to tune things. What we're seeing is that because of the Milky Way's spread optical colors, when kind of viewed face on, imagine viewing the Milky Way face on, in addition to somewhat substantial star formation rate evident at UV and IR wavelengths, the Milky Way's colors are consistent with the previously identified population of red spiral galaxies. So kind of the next direct step that I'm sure you all are now wondering about is, well, we can now perform SED fitting for the Milky Way. We're actually going to be doing this with 2 different softwares because the every SED fitting software works a little differently, so we want to be able to compare results. And with that, we can make a covariate SED for the Milky Way. So what I kind of glossed over is that in the Gaussian process regression, I have these 6 parameters that I'm trained on, but I'm only predicting 1 color at a time. But we know colors across the SED are covariate with each other. So I've actually built a more robust Gaussian process regression now that can be trained on all the parameters we need and also predict all colors and magnitudes simultaneously. That takes into account the covariance between the different colors or brightnesses. And so that's actually mostly done. So we're about to move on to this SED fitting step, which I think will be very exciting. There's also many other cool things that can be done with Gaussian process regression. We've had the idea of perhaps with, say, the DESI sample, because they're getting fantastic spectra, that we could perhaps train from that and make a full predicted spectrum from the Milky Way. that'd be definitely a bit more time and computationally intensive, but could be really great. And tons of other cool things to do with Gaussian process regression. It's kind of starting to become this more emergent tool within astronomy. And now I am a new postdoc at the University of Arizona. And so I've actually kind of started back into working with dwarf galaxies. Some of my work earlier on was understanding satellite populations for a halo like the Milky Way. So now I'm kind of going into the observational side of that. And they're also fantastic tools for studying galaxy evolution, kind of at one of the extremes, as they are the lowest mass galaxies that we have. And of course, you're always welcome to reach out to me if you have questions about things like Gaussian process regression or using my models. The GPR used to construct this SED is publicly available at my actual GitHub page. This is my website. And I think we'll end that here. Yeah, thank you for having me. I will take questions if anyone has them.
Yeah, thanks so much, Catherine. That was a really fantastic talk, and I loved the clarity of your visuals and your plots.
Oh, thank you. I appreciate that.
Yeah. Anyone have questions for Kat? In the meantime, if anyone has more extended questions, I've dropped the link to the spreadsheet where you can sign up to chat with her. Note that she does have availability tomorrow, so it's not just tonight. I guess I have a question.
Yeah, go for it.
Could you give us a sneak peek of what, even if it's just in like words, since I know you're just starting, what you're going to do with dwarf galaxies observationally at U of A?
Yeah, so I've started working on a couple of projects. So one of the things we're looking at is testing satellite planes and some of the nearby large groups. So specifically SED-A, for example, and NGC 253, just trying to understand, do they actually have a planar structure in their satellites or not? So that's something that we observe within the Milky Way, that the satellites seem to fall within a very specific plane around the Milky Way, which is not consistent with what is predicted from your standard, say, N-body simulations, for example. And so we're kind of trying to understand, do we also observe this in other groups, or is it some sort of kind of anomaly that we're seeing within our own local group? So that's one of the things I'm working on. Another thing I'm working on is looking at tidal ultra diffuse galaxies. So UDGs are these very kind of strange objects where they're very large. They have masses almost as large as the Milky Way, but they're also extremely diffuse, very low surface brightness. And the kind of their origins of them is very hotly debated. Essentially, how exactly do they form? So one of the other postdocs of Dave Sand, who I work with, has worked on, he's looked at a couple of these galaxies where it seems to be that they were just regular dwarf galaxies that then got puffed up as they fell into with a companion or into a group. And so I'm also following up that further, where their previous sample, they looked specifically at objects that didn't have UV emission, and now I'm looking at objects that do have UV emission to try to better constrain even further. Do these also form from, are they just puffed up regular dwarfs, or are they maybe things called tidal diffuse galaxies, which are formed from two very large collisions that result in this very kind of diffuse thing with star formation rate, but they don't have things like globular clusters, probably don't have dark matter either, and those are kind of odd objects. Or perhaps one of the many other possible formation scenarios for these wild galaxies. So that's kind of just a couple of the things that I've started working on. There's tons of science to do with dwarfs.
Yes, that sounds really exciting.
Yes, yeah.
I'll be looking forward to seeing some of that.
Exactly. Yeah. I'd be happy to come back again and talk about it once, we finished up a little bit more of the analysis.
Yeah, for sure. Any other questions for Kat?
Yeah, and if you feel, awkward asking questions, again, always feel free to, email me, to reach out. Very happy to talk, even one-on-one.
I guess one quick question. I'm sorry if I missed this earlier, but the fact that in the infrared and the UV, the residuals kind of blow up. Is there like physical reasons as to why that is, or
Yes.
is it like uncertainties, or?
It's generally because of the uncertainties. You can see that here, where the errors are just a lot larger, especially in FUV. It's just these are not as well constrained bands compared to, say, the optical or even the near IR. Yeah, WISE is notoriously bad in W3 and W4. We initially thought maybe we shouldn't use them, but yeah, there's a lot of issues with WISE because we need K-corrected values, as if we want rest frame photometry. There's actually not good K-corrections for WISE, so we actually have to develop our own algorithm for determining the K-corrections, which that paper should actually be out very soon. So yeah, this mid-IR data can be quite tricky to work with, and it's very noisy.
I see. Makes sense. Thanks.
Mm-hmm.
Any other last questions for Kat? Well, so the student-only session will, because this is a later seminar, is going to be held right after here. So students, if you want to chat, just stay on the call. And then, yeah, if you want to chat in more detail with her about anything she's talked about today, I think you haven't talked about at all any of your like substructure,
yes, so
satellites,
also very happy to talk about, dark matter substructure, halo property, correlations, all that. Very happy to talk about one-on-one.
Yeah. So if you want to chat with her about any of that, feel free to sign up on the spreadsheet.
Yes.
And again, the link is in the chat. So yeah.
Thank
Thanks again
you
so much for that wonderful talk.
Yes. Yeah. Thank you for